Good morning, everyone. I'm Kwonyoup and I really delight to have this presentation to talk about a new hope, the one last chance to save your SSD data. We are mainly engaged in business related to embedded devices. We analyze the security threat of embedded device, reports unknown vulnerabilities, and support countermeasure. In particular, we focus on reverse engineering and side channel analysis for embedded device. Recently, we are also doing business related to intellectual property rights using reverse engineering. Today, we will explain the result of conducting research to find out the truth for the SSD data recovery. There are several design limitations to the way SSD drives are configured. Existing types of flash memory allows a limited number of writes of operation before they wear out. Rather than reusing existing blocks of memory, modern SSD drives use smartware labeling technology that writes data stored in one block to another when it is modified. Then blocks containing potentially sensitive information are scattered throughout the memory chips. To further increase the useful life and improve the wearablability of SSD drives, manufacturers install flash chip that can store up to 25% more data than their capacity area. This extra capacity cannot be handled through the operating system or any other reasonable means. Because of this, data on SSD drives cannot be safely erased through conventional means, as required by some government and military standards. To solve this problem, some SSD manufacturers have implemented the extension to the 8A ANSI specification to safely destroy the information stored on all flash chips. Unlike software-based tools, the 8A Secure Erase command instructs the built-in SSD controller that support the command to electronically erase all block on all flash chip in the drive. However, it is difficult for us to grasp the truth about the internal working of SSD from outside. It is frustrating in forensics that erased information cannot be reliably recovered. With wearablability at the beginning of each write operation, a previously unused block of data is used to make extensive use of the drive storage capacity. Repeatedly writing to the same field will cause the entire contents of the SSD drive to become dirty, and the write speed will be much slower than usual, resulting in significant performance degradation. This happens because the flash technology used in SSD drive requires that controller erase block before performing a write operation. This property is unique to storage device based on flash technology and is very different from how traditional magnetic tensorable media handles write request. Since the process the erasing previously occupied block tend to be much slow compared to reads and writes. SSD drive full of dirty block require significant time to write even a single block of data because there are no empty blocks. Because of this, SSD manufacturer design a process that does garbage collection and clears dirty block in the background and make them available again for fast write operation. The problem with garbage collection is that the drive and controllers that don't know exactly what blocks the operating system fields or system structure actually occupy, which block are no longer being used and are just dirty blocks. The controller can display blocks that have been remapped to other blocks as part of the wear leveling process, but this information slows down the drive process, which is usually filled with dirty blocks during normal use of the drive involved in creation. To solve this problem, SSD designers have developed an interface that allows operating system to inform the controller that certain blocks are no longer being used through the trim command. This allows the internal garbage collection to electronically erase the contents of this block to prepare for future write. Block of data processed by the garbage collector are physically erased. However, this also cannot be verified outside of the SSD. In fact, there are not many ways to perform Ssd forensics. The information on the SSD controller and the internal algorithms of the SSD are not disclosed. And for this reason, development of SSD forensic tools is insufficient. Therefore, we took the challenge for the SSD forensics. First, it is to build an environment that can analyze the latest commercial SSDs. This should enable dynamic as well as static analysis in the firmware code. Through the analysis environment, the dedicated algorithm for the process of writing, reading, and erasing internal data by the SSD must be able to analyze. Based on this, we collected the entire data of the SSD and identified the situational conditions for recovering data. The details SSD analysis process and contents are explained by senior researcher Seungjoon.
Thank you. Now I'm going to start by showing SS format reversing. Hi, I'm Seungjoon Lee, senior researcher of SNT Works. I am very honored to talk today. I'm gonna split this talk about SS format reversing into 3 sections. First, I'll explain background information shortly about SSD hardware architecture and security encoder. Second thing is SS format reversing focused on how to access our physical block data. But also it gives prior knowledge which is needed to restore overwritten data on SSD. Finally, I can show you how can we recover the overwritten data if there is hardware-based security encoder. Before we get into that, I'd like to explain why commercial SSD reversing is hard. SSD manufacturers and their controller manufacturers don't want to open their information to protect their technologies. So datasheet is marked confidential and usually only given out after NDA is signed. And also, they might be concerned about misuse by bad guys and end users. Anyway, they appear to protect the privacy of their users, so they have the opposite side of reverse engineer. Let's look at the commercial SSD architecture. The SSDs are equipped with several low-power embedded processors such as ARM and ARC. Generally, mid-range SSD controller adopt a multi-core architecture to maximize I/O parallelism. So, if they should support more channels, control might be made of more cores as well. Although single-core based controller contain all middleware only in a single core. In multi-core based controller, master core only work in host interface, and slave core only work in flash translation and flash interface. The master core and slave core each have their own data memory. Using the IPC, the master core and the slave cores can transfer data over shadow memory transport. And an also important part of this is the host interface logic, which is integrated with security encoder. They usually use AES access. The full data inclusion on SSDs can eventually ensure the security of confidential data. This achieves the goal of each block producing unique ciphertext given identical plain text. As you can see, the block inclusion key is altered per ABA, making the encryption very difficult to break. Here is a rough diagram about hardware-based security encoder. Let me show you guys this basic pattern. If we read a file from SSD, but the SSD controller can handle it only with the encrypted data, until SSD controller throws the data into their host. Anyway, it is not possible to observe the encryption process itself, meaning the user cannot see the encrypted data as data that is read will already have been decrypted, because it is built-in hardware engine. But there are still entry-type controllers have no crypto engine, and the low-cost SSDs manufacturers use it generally. They have released the SSD until now, tend to put this controller for economic regions. But the most of the middle-end SSDs support hardware built-in crypto engine. So the manufacturer touted the controller's ability to encrypt the data with AES algorithm. Anyway, our reverse engineering process could be applied to these two types. Well, now let's get down to details of SSD firmware reversing. In this chapter, we'll show you how to access or physical block data based on firmware reversing on commercial SSD. Although we talk about one model in this time, we would also like to show our reversing approaches not be confined to specific SSD. Then, based on our analysis, we'll be demonstrating our demo which can access or physical block data using PBA manipulation. Please take a look at this diagram to comprehensively understand the read sequence based on our target. As you can see, there are three main components in SSD firmware. So we should find where the three components are in the firmware based on dynamic analysis. The first, we should find the host interface layer part where the data comes in and out from AT interface logic. Second is flash translation layer. It is considered as highlight part of the controller. The last thing is flash interface layer, which is communicated with flash chip physically. After this slide, we'll show you these components and some details of what you found from analysis in our target SSD. It is the first area where stored in the SSD control memory from the host interface hardware logic when you send AT command to SSD. And also it is important area that tells where the AT command starts and where to start analyzing the SS format. As you can see, in this buffer, we can check ATA command, requested LBA, and their ranks, which we sent. We step into code line by line after finding out ATA command buffer. In the code lines related to ATA command, there's table can handle the ATA command which we sent. Look at the right side. This is a table which is indirectly called by ATA command handler function what we found. We can see supported ATA command in this table, such as read and write command from erase and update format and so on. You can see certain code line which can read data from NAND flash chip when the R1 register stored to certain memory address. The address is actually flash chip channel buffer, and this command is enable signal. I will talk about it later. Anyway, after this line, we can check the new multiples of sector size which was updated to flash data buffer. If the target has hardware-based whole disk encryption to encrypt every data, we need to cross-check to make sure if the data is actually read from flash chip. So we pick up any plain text data and write this data to SSD, and we already know the right buffer address where the ciphertext get in, so we can check whether this ciphertext and our readout data before from NAND flash chip are same or not. Finally, we can be sure that this is flash data buffer address. Since then, final process of read sequence is about sending the data read from NAND flash chip to host. It can also show certain code line which stores always high bit to certain memory address. Only after this line, we can show data in host read buffer on PC. If the SSD have security logic, we can get plain text data which is decrypted by hardware security decoder, as you can see. Although we have no idea about the logic, AES-XTS generally, the block encryption key is altered per LBA. To decrypt the ciphertext properly, we should already send LBA corresponding to each ciphertext controller. Only then we've got a match. From now on, I'm going to talk about critical components in the SS format. They are flash translation layer and flash interface layer. To get data from our physical block on SSD, we should exactly know how to make PBAs and send the NAND flash command into channel buffer. So first, we obtain more details about translation mechanism over at LBA to LPN and LPN to PBA in target format. And we figure out where flash chip channel buffer and what their update function to know how to send the NAND flash command. Then we are able to inject the NAND flash command to this buffer to get the data from our physical block. We need to know about LTPMap first. To maintain organization, the controller used mapping table to remap the LBA to PBA. This is LTPMap. Generally, in multi-core controller, each slave core has own LTPMap tables on each channel. From what we found out from our target controller, a channel supported controller have their own each LTPMap table. We could also check these tables are stored in NAND flash chip actually. So whenever power up, the controller loads these tables to their data memory. If we can access our physical block, we can also handle all the LTPMap tables stored in flash chip directory. This slide shows LPN to PBA translation part on our target SSD. The LPN value refers to each element which are in LTPMap tables. Generally, the ranks of LPN value is decided by SS mapping algorithm, and capacity and flash chip is adapted by SS frame manufacturer. So we need to know how the LPN is organized. We just found scattered PBA calculation code in format. We built into the one logical expression is easy to understand. So you can see 3-piece PBAs. And then we should know exactly what they are. Actually, NAND flash die is comprised of planes which contain procs, which contain pages, which contain individual set of data. Although we do not get to come across a confidential dataset, Judging from the size of their bit, PBA1 is block and page address which are concatenate with 1. So part of 7 bits is PBA1 indicate page address, so they contain 828 pages in a block. And the part of 13 bits in PBA1 are block address, so they contain 8,192 blocks on frame. We are not sure whether it is way number from PBA2 and PBA3 in this code line. Based on our fresh command analysis, which I talk later, PBA3 is most probably frame address, so the other one is PBA to indicate the way number. On a side note, and also you can see resolved block count on translation part. In our firmware analysis, the way to make a prohibited area in the SSD is just to grab resolved block number in FTL. So user cannot access these blocks by factory setting. In some cases, the AES key already generated by factory, which is then stored in NAND flash chip and is only known by drive itself. For lack of time, I will not deal with that details in this talk. Go back to the topic. The next step, we need to find the absolute address of flash chip channel buffer. If we know the address, we can use this address to send the NAND flash command. This memory area shows flash channel's buffer address, what we found. There are 4 channels in the slave core, and you can see that there are a bunch of interesting data divided into 2 parts in one channel. The upper part command is related with parameters such as flash addresses, and the other one is primary command, which are parameters to be passed to flash chip. Next slide, I'm gonna show more details about this, what it is. The SSD allocate absolute address for flash command transfer. It seems like a waiting room or data bus for connecting with their flash chips. So in this channel buffer, there are trigger signal which can start the commands to enable NAND flash chip. So you can see the PBAs which are derived from LPN to PBA calculation part. And there are commands read in no direction according to read or write command, and read buffer address. This is read in no where will be stored on control memory after readout from NAND flash chip. So when after they complete the command, readout data are in data memory address. This is demo which demonstrates access or physical block on SSD using PBA manipulation, even if it is securely erased. Before the test, we do secure erase for clean and write arbitrary data on host space LBA0 to end of LBA. There are 8 LTP map tables, and you can see our LTP maps are updated with new LPN. Now this time, we retry secure erase command, and it will soon complete the command. Then you can see also changed LTP map. It just changed with our high bit value on maps. It means invalid or factory initialized LPN. So if after SSD fully erased by secure erase, you cannot get access to flash chip in memory because it cut off physical route to go flash chips. Even in such a situation, our tool knows where the flash chip channel buffer is and how to put the PBA elements, so we're able to get our physical block data in NAND flash chips. You can see the data file which is gathered by our tool. So what can we do with it? In non-security encoding model, it will identify unique PBA block data not found in the LBA. So it will get our plain text data on flash. Second is it is used as forensic tool. I think forensic guy need image which based on physical address on SSD. Furthermore, it is non-destructive, If SSD have security encoding, it is used as verifying of secure erase or data wiping tools. In commercial SSDs, when it full erased with secure erase, the controller cannot remap the LBA to PBA because they cut off physical route to go fresh chips. However, it can make it possible to get data even such a prohibited area in the fresh chips, so we can verify whether SSD still leaves sensitive data or not. And also, we have talked before about how SSD manufacturer control reserved physical block in FTL. We think that there may be critical information in this area. In this chapter, we will show you how can recover the overwritten data if there is hardware-based security encoder in SSDs. This illustration shows what happens on SSDs when overwriting to the same LBA. This could be a case by mistake or on purpose, such as ransomware, where you can see the old data that is already stored on flash, and their physical data have a unique RPM value to tell controller where those stored in flash. Then if we overwrite new data to the same LBA, the new RPM value will be generated by FTL component, and the component tries to overwrite new RPM to the LTPAP table. The old RPM is overwritten with the new RPM value on LTPAP table, then controller no longer know where the old physical data on flash chip, so we cannot get the data before the overwrite occurred. As you can see, SSD controller just cut off their physical route and the data still arrive. If we can access our physical block on flash chips, so we'll be able to get previous data before overwritten. However, if the target has hardware-based whole disk encryption to encrypt every data, although data still arrive, we can get only usually encrypted data. However, we still have one last chance. If we can figure out old LPN from the current LPN, we can get plaintext data. It means that we should send LBA corresponding to the encrypted block to SSD controller, and then it would be decrypted properly. However, it is hard to know LBA corresponding to the given LPN because LPN do not contain any information about LBA. It is the same question about finding LBA corresponding to ciphertext. However, at least for overwriting situation, we can get plaintext to easy, even if we don't know master key. Since it is easy to know about LBA from current LPN, so if we can reconstruct all the LPN from current LPN, the ciphertext can be decrypted naturally with control. Anyway, the challenge is to find what all the LPN is. To reconstruct old LPN, we should know how the target SSD select the block number when we overwrite. And then we also need to know how page number is changed according to the overwriting. When we write data to in our target SSD, we figure out that flash translation logic has block aging table, which block has been used many times to decide block number. The simple diagram on the left, it shows block aging table and how they work. So if we write data, FTL component calculate average of aging count on the table, and search the smaller value than average count to search less frequently used block. Finally, the block number is stored on LTPAP table, and after, if the block somewhat used, it is stored in their tail. Now, this time about page number. If an application write file to the same LBA, this is also changed depending on the number of occurrences of write on same LBA. Look at the diagram on the left. When you overwrite to the same LBA, you can see the page changes following the number of write count. Here in LPN, as I said before, the lower 7 bits is offset value which indicate page. Especially, you can see only the offset value increase depending on the number of overwriting in the same LBA, as only offset value is increases depending on the number of overwriting, so you can also see only the page is just moved and newly written. Where it is default feature of SSD using the block level mapping algorithm, when after overwriting occurs, the original page is marked as stale, and there is no choice but to leave it as it is. Because erasing cannot be processed per page, it is done by block size. Therefore, the GC function generally erases all the pages together at once. Furthermore, to extend the SSD lifespan, SS tend to avoid aggressive it until there is not enough space, so we have still time to undo. We can expect the data will remain. Before our demonstration, I will briefly explain ransomware, which is among the very worst disaster. The key here is also how to find the original data before overwritten occurs in SSD. From a file system activity view, based on how it encrypts data, ransomware can be divided into two groups, overwrite or copy. Copy-based ransomware, their encrypted data is stored on free available sector, in other words, copy and delete. In this case, it is possible to recover some original data with the conventional data recovery tools. However, overwrite type, that encrypted data is stored on the same physical sector, so it is impossible to recover with the tool. Because the SSD uses other physical block when the ransomware writes on identical ABA with the encrypted data. Since then, update to new LPN, so original data get lost their physical root. So we should open their physical root by old LPN restoration. In next slide, we will show you about our steps for overwritten data restoration. These are our steps for data restoration. First step is that we should get ABA from the file what we hope to recover. If you use commercial disk editor, such as WinHex, physical sector is ABA in terms of the hard disk drive. Yes, it is very easy to find out. Second step is that we should get APN corresponding to ABA. Third step is recovering all the APN using our script. We deduce all the APN from the current APN based on aging table and their write count. And we filter candidates likely to have been used. Final step is that we replace current LPN with candidate LPNs, and then we read again this file, and it would be decrypted with original ABA. If that file is not the file we are looking for, in this case, we retry attempt to replace LPN with the other candidate LPNs. Probably we can find the file what we sent. Here is a simple demo which demonstrates overwritten data restoration of a file. Firstly, we format the target SSD with NTFS. In the D drive, we make a test file which will be encrypted by ransomware. We write something text for demo. And save the file. And we get ABA from the file using WinHex. So you can see physical sector in terms of a hard disk drive. This is ABA in SSD view, and you can see file content. And we just encrypt the file with overwrite type ransomware simulator. And then you can see plain text data before encrypt and encrypted text. And this is LPN value, which is we have to restore later. And after ransomware overwrite to same ABA, same file. And it is done, you can see changed LPN value of the file. And after we guess their old LPN to doing so, we filter candidates which are likely to have been used. You can see the previous LPN value among our old LPN candidates. We just read the file. You can see encrypted data yet. And on the right, you can see also LPN of encrypted data. Final step, we should replace current LPN with old LPN. What you got before? And then we read again this file. You can see the file previous data before ransomware occurred, and it is decrypted properly. What is next? We work on the analysis for various vendors' SSD are now in progress. So we have a plan that the work will also be expanded to cover as much as possible to the other SSDs. And the usage of NVMe type is increasing. It is worth applying to NVMe type for future. For enhance our tool, we need to more study state-of-the-art SSD technologies, and we are preparing security evaluation tool for SSDs such as commercial wiping tools or manufacturer secure erasing command verifying tool. For the other SSD security evaluation, we work on commercial SSD AES key extraction using side channel attack. As you know, conventional forensic tools still focused on hard disk drive, so in the future, we should our tools may need to focus on the forensic tool for SSDs. So we are looking for their needs. And also, I think that further study about the relation between French translation layer and security is needed in this area. Thank you for your attention. If you have any question, please send me an email. Thank you.